presenting some of my research using surface pressure and concentration correlations to improve urban air quality. So I'm sure we all know urban air quality is a big problem, especially in cities where populations are high, and increased population or increased pollution leads to higher rates of respiratory and cardiovascular health conditions. So this is kind of the high-level motivation behind my research, which is looking at experimental methods, so specifically wind tunnel simulations of pollutant dispersion in urban areas. I'm looking at experimental methods because conditions are fully controllable and repeatable, and they allow us to simulate all the scales, which are kind of the main advantages over fieldwork and numerical simulations as well. So a more specific introduction to my project in particular. So current experimental methods measuring concentration in wind tunnels use something called a fast flame ionization detector, but this apparatus is large, expensive, complex to use, and quite limiting in the fact that you can only measure concentration in one location at a time. On the other hand, surface pressure is much simpler to measure. The sensors are much cheaper, and you can use lots of them to measure surface in lots of locations simultaneously. So the hypothesis of my research is whether we can use surface pressure as a proxy for concentration measurements. The basis behind this hypothesis comes from the fact that the convection term of the transport equation is governed by velocity, and then Bernoulli's equation also tells us that pressure is proportional to velocity. So it's a kind of logical conclusion that there'll be some sort of correlation between pollutant transport or concentration and pressure. I just need to find a way to characterize this. So this is where the smart cube comes in. The smart cube is an experimental model building. The building is a kind of cube shaped, and it has 500 pressure taps logarithmically distributed over its surface, concentrated in regions where pressure gradients are highest. So each of the pressure taps on the surface of the cube are connected to an individual pressure transducer in a case with a length of silicon tube. So that was a fun week making that. But the case fits underneath the wind tunnel, and then the cube just needs to sit on top of a hole in the tunnel floor for all of the tubes to fit through. So that was the idea behind the model. The tubes, however, mean that there is an amplitude attenuation of your pressure signal and also a phase lag between the pressure change kind of happening on the surface of the cube and that being detected by the pressure transducer. So we needed a way to compensate for this effect, and we developed a dynamic pressure calibration system to compensate for this tube effect that we saw. So we subjected the cube to a range of different pure tone frequencies from about 2 Hz to 200 Hz, and then compared the response from each of those individual pressure taps attached to the cube to a reference pressure sensor attached with a really negligible length of tube. So then we got a calibration constant for the amplitude and the phase for each of those pressure taps on the cube, and then we correct them all individually to match that reference one. So on the right-hand side, you can see the effects of our correlation, and just about. So yeah, each of them are calibrated individually to compensate for that effective tube. So that means we're able to measure instantaneous pressure simultaneously all over the cube. So kind of a last slide on my methodology. This is a picture of our setup in the inflow tunnel. So the inflow tunnel at the University of Surrey is capable of simulating atmospheric conditions with upstream roughness. And then the smart cube is in the center of our turntable, so we're also able to simulate different wind angles. And we have an upstream pollutant source releasing propane. So we can move that around, and then the fast fit measuring concentration is on a traverse, so we can also measure concentration at multiple locations, but only one at a time. And then the last part of our setup is this cube array with these kind of dummy cubes to simulate a more realistic urban geometry. So, as you can imagine, with so many pressure sensors, I have a lot of data. So the results I'm presenting today is kind of the simplest case only. So just the single cube at 0 degrees. I haven't massively analysed the more complex cases yet. So the first step is to validate our cube. We do this by looking at the mean pressure distribution. So when you're looking at this, imagine you're kind of looking down on top of the cube and the sides have been folded out. And then this is the coefficient of pressure calculated with the free stream velocity. So you can see the highest pressure is on the front face of the cube, so side one is facing upstream, and you can also see the separation region with the negative coefficient of pressure. So kind of what we'd expect. The next part of our validation was to compare this data to published results from literature. So we compared it to some previous experimental cases and some fieldwork data as well. So this is kind of the cross-section across the top of the cube and also horizontally around the midsection of the cube as well. And our setup is most similar to that of Castro B in these graphs, where they simulate a neutrally stable atmospheric boundary layer. And you can see it agrees fairly well. The differences are likely Reynolds number effects, but this kind of helps us know that we can trust our cube going forwards for the rest of our analysis. So we're moving now on to the kind of the novel capabilities of the smart cube. So this is the standard deviation of pressure. So this is using the fact that we're able to measure instantaneous pressure fluctuations because of that calibration, dynamic calibration that we've applied. So here you can see that the highest standard deviation is kind of the top corners of the front face. So that's the kind of the area where we see the most fluctuations in pressure, and then also in the separation region. So yeah, again, this is possible because of that calibration we've applied. So moving on now to incorporate the effect of the concentration and the pollutant source that we have in our setup. So this plot is just the front face of the cube, so the upstream face facing the flow, and this is a plot of the correlation coefficient between the pressure on that side of the cube and the concentration in one location marked with the white cross. And for this case, it was just a single cube, 0 degrees, and the source is 1 cube height upstream in line with the middle of the cube. So the magnitude of the correlation coefficient might not seem massive, but the fact that this isn't kind of random or jumbled indicates that there is something there. We are seeing some sort of correlation between these two parameters. We just need to kind of understand it a bit more. So the strongest, next to the FID, we're seeing a really strong negative correlation. So that's what we're going to look at on the next couple of slides. So this slide here is a cross-section of the concentration. So just upstream as a front face at 3 Y locations, we're plotting the mean concentration in black. And then the other colours are kind of the concentration sampled based on the instantaneous difference between the two parallel sides of the cube, which should give an indication of the plume kind of meandering in the flow. So there's not much you can conclude from this other than the fact that the mean being asymmetric means that our setup wasn't perfectly symmetrical. So either the source wasn't perfectly in line with the middle of the cube, or the source or the cube weren't at exactly 0 degrees. So kind of hard to deduce much from this, but on this slide, I've subtracted the mean and non-dimensionalized the concentration. So if you look at the purple line, this is the highest pressure difference between those two sides, which indicates the pressure is highest on side 2, so the negative side or the negative Y direction. So that's when the pressure is highest in this direction where concentration is lowest, and then vice versa for the orange. That's a low pressure difference, so the pressure is higher on side 4 in the positive Y direction where we're seeing a low concentration. So that kind of supports the negative correlation coefficient we saw on that contour plot, that when pressure is high, concentration is low. And we think that's because, imagine you have like kind of a slow parcel of air moving past the source, it's going to collect more pollutants in that pocket of air. So when it reaches the cube, it's got, whichever way around, higher concentration, lower pressure. So I think that's what's happening. One more slide to kind of indicate that there is some sort of correlation going on. This is just a very short section of a time trace from concentration and an adjacent pressure tap. So I've flipped the pressure to try and make it more visible that there is a correlation. Not at every moment in time, but generally, I think you can agree that they match somewhat. So to bring you up to speed with my latest analysis, so this is the very fringes of machine learning, very preliminary data. But the idea here is I've used a 5-minute time trace of pressure everywhere and concentration in one location, and I'm kind of trying to prove that we can reconstruct a concentration sample from just pressure data. So I'm not at the point where I'm trying to kind of predict concentration, but just reconstruct that characteristic concentration sample, which is very spiky, so not the easiest thing to reproduce. But this is using just 10 pressure taps with the highest correlation, and the relationship between those 10 pressures and one concentration to produce the bottom graph, which vaguely looks like the top graph, not instantaneously, but heading in the right direction. So just to bring it to a close, my conclusion so far is that a correlation does exist, and we can infer some information about concentration from pressure measurements, but there's still a long way to go before my final goal, which is to be able to predict instantaneous concentration fluctuations around the cube using that relationship between the pressure everywhere and the concentration in one location. So I've got some data where I've got 2 concentrations, and I want to use one to predict the other one. And then the application of this is to be able to simplify wind tunnel studies with a view to improving urban air quality. And maybe one day these techniques could be used in field observations as well, because pressure is also easier to measure in the field than concentration. So, thank you.
No. Thank you very much, Joy. That was very interesting. Do we have questions in the room?
Hello, thank you for the presentation. I know you said at the end that you're focusing on trying to get the instantaneous fluctuations. I've kind of, in the last year, been looking more into air quality, and I've noticed that they use a longer averaging time window for some of the concentrations they're measuring. Have you explored results on longer averaging windows, and how well do they correlate there? Do they correlate better? Are they worse? Or
Is that in field work typically?
no, I'm in my context. I am looking at like 24-hour PM 2.5, which is really long averages compared to the results you're showing. But that's normally, in terms of regulated data, that's what
so my first experimental campaign, I think I did all of my concentration samples I just measured for 30 seconds, and then later realised that that was nowhere near long enough. So we then did, I think, 20-minute samples at each location, and I kind of plotted at each minute the like contour plot of what was happening, and then I realised that it was about 5 or 6 minutes where it stopped varying so much between. So yeah, I did some 20-minute samples and concluded that 5 minutes was enough to get a good mean concentration. But it's probably different in a wind tunnel to 24-hour PM 2.5.
Thank you. Very good. Yeah, I mean, there's of course the question of understanding where the pollution is going and then the overall distribution over the day, but we need to understand also the details. I think it's very good. So, shall we ask the second speaker?